All right. Hello, everyone. Welcome to today's Corundum developer meeting. Thanks for finding the time to tune in today. Let's see here. Main thing I got is status updates after just announcements on the next meetings as usual. So the next Corundum developer meeting will be July 3rd, and the Switch developer meeting will be June 26th. So you can mark those down on your calendar. All right. So status updates for this week. Mainly we got the PCI Express RX buffer management, which I'm pretty much done with. I got to run a couple of additional tests just to make sure that everything looks good with respect to that, and a couple things have to be merged back upstream into Corundum. But that's pretty much squared away at this point. I've made some updates to Icebridge optical module interfaces on a couple of boards. Basically everything that used the mod cell pin to determine which module to talk to. That hasn't worked until now, but I finally came up with a simple solution for that. Well, relatively simple solution that seems to work well both on the hardware side and on the Linux side. And then there's also some kind of future stuff that I want to talk about today, and just, I was hoping for people, but and just to kind of see if there's much interest in the community. So 40G Mac, I'm not sure if anybody wants to help with that. Put something together, and then I'm also thinking about implementing support for at least some lower speeds. Gigabit, I think, would be probably the most interesting. But there are other standards as well that might be worth thinking about. And then I know at least Carlos is interested in TSN support, and one aspect of that is frame preemption. I was reading over the spec for that over the past week or two just to kind of get my head wrapped around it. So I'm going to briefly talk about that. And then we're also starting to take a look at White Rabbit and potentially PTM support as well. So I'm going to mention a few details about that. Just, again, see if anybody's interested in any of this stuff. So let's go through these points one by one. First thing, the PCIe RX buffer management. So I talked about this a little bit last week, but had to compress it because of a guest presentation. So today I'll go into a little bit more detail, and I also have some measurement results that might be interesting to take a look at. So in a PCI Express system, the endpoints have to advertise infinite completion credits for the completion data for any read requests that have been issued. So this is done to prevent deadlocks, but the flip side is it means you can't put any back pressure against the incoming completions in the RX direction. PCI Express IP cores have to have some amount of RX buffering because you might have to deal with some back pressure from the user logic, or deal with rate limiting, or not rate limiting, but rate differences, things of that nature. And there's also kind of a TLP replay protocol, so you got to make sure the TLPs are valid before the user application can deal with it. So they have to be buffered for a little while. But since there is no back pressure for completions, because you have infinite completion credits, there is a possibility for that buffer to overflow. So to prevent an overflow, you have to manage how many read requests are outstanding to prevent that. So previously, the Corundum DMA engine didn't do this, and some of the previous suspected PCI Express hard IP core bugs were, well, probably just completion buffer overflows. So yeah, it's time to implement this because we're running into this problem. So the question then is, how do you implement this? So the first thing is you got to assume that the PCIe IP core can store some number of headers and some amount of payload data. So generally the headers are tracked as, header credits, where one credit means one packet, and some amount of payload data, where the payload data is tracked in terms of data credits, where one data credit is 16 bytes of data. Although I guess it's not so much 16 bytes as 4 D words because PCI Express is a D word oriented protocol. So what we then need to do is track the number of completions and the amount of data credits per read request. The thing that makes this slightly complicated is that read requests can be split, so we have to assume the worst case. And the splitting is done by whatever component we're talking to. So we don't have control over that. We got to assume the worst case in terms of where and how many splits are going to be returned. For PCI Express, reads can only be split on the read completion boundary. For endpoints, that's 128 bytes. For the root complex, that's either 64 bytes or 128 bytes. So the worst case, for every 64 bytes of read data, we're going to get another completion. So, well, plus potentially an additional one depending on the alignment. So, for example, a 512 byte read request could result in a maximum of 9 completions, which is a lot of completions. So, the next thing we need to know is how big the buffers are on the devices. So, looking at the documentation, Intel Stratix 10 provides, with the H tile and the L tile, provides about 770 completion header credits and 2,500 data credits. These are pretty reasonable numbers. If you take a look at the ratio, you get about 52 data bytes per completion. For the Intel P tile, you get a bit more, 1144 header credits, 2888 data credits. It's about 40 bytes per completion header credit. So again, pretty reasonable. But the Xilinx numbers are a little bit weird. For Vertex 7 at Ultrascale, the datasheet lists 64 completion headers and 15,872 bytes. If you take the ratio, that's 248 bytes per completion. That's potentially a problem because you're going to run into the header credit limit long before you run into the data credit limit, assuming that you follow the instructions in the Xilinx datasheets and assume that all of the operations are going to be split every 64 bytes. For Ultrascale Plus, the situation is basically the same with 128 header credits and 32,768 bytes. So double the buffer size, double the header credits, but you can still only use a small fraction of the buffer because the ratio is the same. The Intel figures, everything looks reasonable there. The Xilinx figures don't make sense. So the question is, how does it actually work on the Xilinx devices? So the PG213, the manual that talks about the PCIe cores on Ultrascale Plus, lists the buffer size as 128 CPH and 32,768 bytes CPD. It also says that all the numbers are in credits, so why it's listed in bytes, but the text says credits is perplexing. With RCB 128, 128 completion headers corresponds to 16,384 bytes, which is half of the buffer, and RCB 64 is 8 KB, which is a quarter of the buffer. So with these numbers, you're never going to be able to use that whole 32 kilobyte buffer, assuming you follow the instructions in the core manual in terms of how you're supposed to do the buffer management. So what gives here? Is this a design problem? That whoever designed the core doesn't know how PCI Express works, which I guess that wouldn't be too surprising. Or is this a documentation problem, right? Left hand, right hand, doesn't know what's going on. They put the wrong numbers in the documentation. Not sure. We have to investigate to figure out what's going on here. A few interesting observations, though. On the Vertex 7 manual, there seems to be different numbers of header credits reported depending on which version of the manual. So older version reports 32, newer one reports 64. Not sure why. It also seems like the core uses external block RAM for completions. Unlike the Intel devices where everything's all integrated onto a single external tile where you can't see anything internally, Xilinx device uses a, the block RAM, the PCI Express hard IP core block is connected just to normal on-chip block RAM. So we can actually take a look at that in the implemented design view in Vivado and take a look at how much memory it's using. And in this case, for Ultrascale Plus, you get two banks of, you get two blocks of what appear to be kind of two bank RAMs. And each RAM is 512 by 144, so you get a total of 32 kilobytes plus parity. And that makes sense, right? That matches with the 32,768 data credits, or 32,768 bytes of completion data indicated in the manual. So that seems straightforward enough. The other thing that I noticed as well is that whenever we had these suspected buffer overruns, that resulted in based garbage completion headers. It wasn't just simply the TLP disappeared, and we didn't see like duplicated completions. We saw garbage, which indicates that the completions are probably being stored in the same RAM, or the completion headers are probably being stored in the same RAM as the data, and that under certain conditions, the completion header is being overwritten with payload data. And I verified this with the ILA, not just in terms of the garbage completion headers, but I took an ILA and I dropped it on the signals that go to these internal block RAMs. And we can see very clearly that there is a PCI Express completion header being written into this RAM. So this confirms that, yeah, the completions are being stored along with the data in the RAM. And this further means that the instructions in the datasheet are wrong because the value that they supply for the buffer size actually applies to everything that goes in the buffer, not just the completion data. So it's incorrect to take this 32,768 bytes of data and convert that to 2048 completion data credits. So what's the proper method for dealing with this? Well, method number one is to partition the buffer. We can take that 2048 block, or 2048 data credits, and we can split that out into some number of header credits and some number of data credits. And as long as we limit, each of these separately to these two limits, the sum of those is going to fit into the buffer. So as long as we don't overrun either of them, we'll be fine. The second method is to consider, I guess, what I would call buffer credits, where we're going to basically add the header and data credits for each packet together and consume this single credit type. It basically has the same effect as this partitioning, where you can't go over that kind of combined credit limit. But it potentially allows you to use more header credits if you have a lot of small requests being issued that don't consume a lot of data credits. But it is a little bit more complex from the hardware implementation standpoint because you got to add these things together. So potentially the timing performance could be a little bit worse. But the next question then is there a limit on the number of completions that can be stored in the buffer? We could look at the implemented design to see how big the buffer is in terms of how many memories are used, but is there anything else going on that could limit how much we can put in the buffer? So what we need to do is perform some kind of a measurement to try and make this determination. So what I did is I took the DMA engine example design and I added a mechanism to block the RC interface, and I also added request and completion counters. So then what we can do is with the RC interface blocked, we can issue a bunch of DMA reads. We can wait for those reads to complete, and we can unblock the interface and let the completions be processed by the DMA engine and see if the DMA engine hangs, basically. And then I tested this on two different computers. One of them is my main development machine that seems to like producing max payload size completions. And a max payload size of 256. And I have another machine, a rather old machine. I don't know exactly where it came from, but it's been sitting around for a long time. And that seems to like producing completions of 128 bytes in size, which is convenient for this particular use case because we need to generate a lot of completions. So smaller completions, that's better. All right, so with that being said, I ran several different tests on both UltraScale and UltraScale Plus FPGAs installed in both of these machines just to see what things look like. So the first test that I did is I issued a bunch of small read requests just to see if I could issue up to the tag limit that's ostensibly supported by the core. So on UltraScale, I issued 64, and I checked to make sure I didn't see any back pressure from the core, and checked to see that there weren't any dropped completions. So that was fine. And I did 256, which is the tag limit for UltraScale Plus, and that worked fine on UltraScale Plus. So this has already told us one interesting piece of information, that we can actually send 256, or we can actually store 256 completions in the buffer for UltraScale Plus instead of the 128 that the documentation would imply. And then what I did is I issued 512 byte read requests. So on UltraScale, with the host that produces 256 byte completions, I was able to send 30 of them. If I send more than that, if I send 31, then it hangs. So 30 of them are okay, 31, it crashes. So that's, that's 32 would be 16 kilobytes. So that's about 15 kilobytes, right? And that's 60 completions. So if you go to 64, well, it crashes. So that makes sense, considering that the headers are also stored in the same RAM as the data. Once you fill up the entire RAM, then stuff gets dropped. Okay, so that makes sense so far. And then I ran that same test on the host that produces 128 byte completions. I was able to send 16 512 byte read requests. As soon as you send 17, it doesn't work. So this one, it's okay at 64 completions. As soon as you go beyond that, it crashes. So that makes sense. We're hitting the 64 completion limit. On UltraScale Plus, running those same two tests, the same test on two different machines, I got 62 512 byte read requests, which is 62 requests and 124 completions. So this one is definitely filling up the data buffer. We're definitely not running into a completion credit limit. And then I ran this again on the host that produces 128 byte completions, and it topped out at 232 completions. Again, it's filling up the data buffer. We were able to send more completions, or we were able to handle more completions, but the completions, but it was less data overall because all those headers took up more space. So again, this is pointing to the fact that since this is we're commingling the headers and the data, we have to take that into consideration with the limits. All right, and then I realized something. It's like, well, okay, on this host that likes to generate 128 byte completions, what happens if we issue a request that is just slightly larger than 128, starts right before 128 byte RCB and ends immediately after the next 128 byte RCB? What happens in that case? Is that going to give me 3 completions? Well, it turns out it actually gave me 4 completions. So if I issue these unaligned 136 byte read requests, one read request results in 4 completions. So that actually means you get an average of about 32 data bytes per completion, which is way better than I was hoping for. And this actually ends up being a super good test. So for the Kintex UltraScale device, I was able to issue 17 of these read requests, which corresponds to 68 completions, interestingly enough, and not a whole lot of data. So somehow, I'm still not quite sure how I was able to go over that 64 by a little bit. If you go up one more, that corresponds to 72. Somewhere along the line, that overruns the buffer somewhere. But this is nowhere near filling up the buffer. So we're definitely running into the completion limit. And then into the packet limit. And then again with the UltraScale Plus, I did the same test again. I was able to send 67 of these guys, which corresponds to 268 completions, which again, that's above the what I was suspecting the limit would be at 256. So yeah, that's rather interesting. So I'm not sure why this is going beyond the what I suspected the limit would be, but it is nice to see that we could definitely get 256 completions on the UltraScale Plus devices. It is annoying to see, though, that we do have that limit of 64 on the UltraScale devices, because there's really not a whole lot we can do about that, and that's definitely going to result in lower throughput. But these are older devices that only support up to Gen 3x8, so I guess it is what it is. So yeah, conclusions from those measurements. The ultrascale definitely has a limit of 64 completion headers. So the documentation is correct in that regard. In ultrascale plus, it definitely supports at least 256 completion header credits. So the documentation is wrong there. This is still not enough for the buffer size, even though it does correspond to a ratio of 128 data bytes per completion, unless the RCD bit is set, in which case there should be not much performance, in which case we should be able to use the whole buffer size. But unfortunately, it seems like most hosts don't set the RCD bit because they can, under certain circumstances, presumably split stuff on 64-byte boundaries. So not so great. But one thing to note is that the data buffer size on both definitely includes the completion headers. So the documentation is not correct about the buffer size, or it's correct on the buffer size in terms of, yeah, that's actually how big it is in terms of bytes, but it's incorrect in terms of how to manage that buffer space to make sure you don't get overruns. So what I've gone ahead and done is implemented the credit tracking in the DMA engine based on the packet FC technique described in PG213. I connected the RCB status signals, and for the Xilinx devices, I implemented the credit count limits as per the core documentation, and everything looks good in terms of performance. On ultrascale, I went ahead and implemented that as 64 CPLH and 1024 minus 64 CPLD. On ultrascale plus, since it definitely seems like we can use 256 header credits, I went ahead and implemented that as 256 CPLH and 2048 minus 256 CPLD. Unfortunately, it seems like there is a little bit of performance penalty if we only have 256 header credits, but I don't think there's much that can be done about that unless we're going to say, assume that under certain conditions, we're going to be getting packets that are on average larger than 64 bytes. And or we're not going to get very much back pressure. So I don't know. We'll roll with this for the time being. Take the conservative approach and potentially revisit this later if that performance penalty ends up being a problem. I guess in terms of status here, it's mostly updated in the repository. What I do need to do is run the same tests on the Intel on basically all the boards with the limits set in the hardware, just to make sure that nothing gets dropped. So I've run it on the Xilinx boards, but I have not yet run it on the Intel boards. So I'm hoping to do that today or tomorrow to get that finalized, just to make sure that everything looks good. I guess the thing that complicates things a little bit on the Intel boards is that they don't have a separate RC interface, so I have to block the entire RX interface, which means I can't read anything from any of the internal registers until, waiting and removing that block. So anyway, that's the status with the buffer management. Moving on to the Icebridge C optical modules. So on some boards, the mod cell pin is used to select between QSFP plus or is used to select which QSFP module is being addressed. So I originally attempted to use the Icebridge C regmux driver in Linux to talk to it or to control those bits, but unfortunately that module takes out a module lock and makes it hard to reload the NIC driver. Basically have to go through and manually detach all of the PCIe devices, which releases all of the module locks from the Icebridge C regmux driver, and then you can actually RM mod the main driver and reload that. So then what I decided to do is, well, hey, this already works with the Linux can talk to the Icebridge C mux chips on the board just fine. So, well, what if we implement an Icebridge C virtual mux chip inside the FPGA? It's literally just a single register that you can poke at over Icebridge C. So doesn't sound that complicated. So I went ahead and wrote a basically single register module in Icebridge C. And then what we can do is take the state of that register and drive the mod cell pins on the QSFP modules. So this mainly affects 5 different boards: the Alpha Data ADM PCIe 9v3, 2 of the Cisco boards, the K35P-S and K3P-S. Actually, I guess I should say that those boards don't actually use mod cell pins. What they do instead is have 1 SCL and 2 SDA lines. So each module has its own SDA. So what I ended up doing is basically mapping that into mod cell. So depending on which module you want to talk to, it'll use one SDA line or the other. So that works with this scheme. And then 2 of the Intel dev kits had this issue as well: the Agilex F dev kit and then also the Stratix 10 MX dev kit. Another thing that I noticed is after implementing this is that it seems like some optical modules are slow to respond to the mod cell pin, probably because they have a microcontroller in there and they get check the mod cell pin periodically, and if they see the mod cell pin set to select the module, then they have to go in and enable the I2C interface or something, and I guess there's some latency with that. So I think the optimal solution for this would be to add some delay between selecting the flipping the mux and actually trying to access stuff behind the mux. But it seems like there's no easy way to add that in Linux because of how it manages the muxes and whatnot. You can't just select them. You basically, because Linux is managing the mux for you, you can't select one of the ports and then wait and then perform an operation. The port is selected as part of performing the operation. So there's no real easy way to add kind of an explicit delay. So if we drop the Icebridge C frequency by 10x, it seems to work. I tried a few other factors. 2x doesn't work, 5x doesn't work, 10x works. I tried, there's no way to add an explicit delay. So hopefully once we have like the management software implemented and all of this is managed by the management software, then this won't be a problem because we can have that thing wait for a couple of milliseconds or something after selecting the module to actually talk to it. So this has been updated in my development repository for these boards. So hopefully that'll make its way upstream relatively soon once I do a bit more testing and polish off the PCI Express modifications. All right, so moving on to some of the future looking stuff. Sounds like there was some interest in the last switch development meeting for potentially having a 40 gig Mac. I have bounced around the idea of building a 40 gig Mac and potentially 100 gig Mac at some point, but it hasn't really been a high priority because we can run at 100 gig using the hard Mac blocks, and seems like either we're going to be running at 100 gig or at 10 gig or 25 gig. I did some poking around, and there is at least one open source 40 gig Mac core, but I have not been able to find a core that also includes the PCS layer. And the PCS layer for 40 gig is particularly important because that does all of the lane bonding and whatnot. So without the PCS core, the Mac core is, I don't know, not super interesting, not super different than at 10 gig or 25 gig. So there is one core on GitHub that ostensibly supports 10, 25, 40, 50, and 100 gigabits per second, but it doesn't have a PCS layer, and apparently it is quote unquote not intended for synthesis. So I'm not sure exactly what that means. Is this thing just intended for simulation? Does it not work from a timing perspective? I don't know exactly what that means. I mean, obviously without the PCS, it's not particularly helpful, but yeah, so it could at least be useful as a reference. So the question here is there anyone in the community that might be interested not in having a 40 gig Mac, but in helping to build a 40 gig Mac and PCS? I don't think this one would be crazy complicated because for the most part, the 40G Mac will run without RSFEC, or it doesn't support RSFEC, and I think the Firecode FEC is optional. This is in contrast to 100 gig, where there's a fair number of devices that won't bring up a link at all unless you have RSFEC enabled, and RSFEC is rather complicated to implement. So that was one of the reasons I didn't really go down the path of building 100 gig Mac. It's like, yeah, I'm not going to build an RSFEC implementation for this, and we have the hardcores that do that. So 40 gig Mac, you do have to deal with virtual lanes, but only 4 of them. So not sure if anybody's interested in that. If you are, let's talk about it on Zulip, and maybe we can get the ball rolling on that, because that could be a fun project. All right, and then kind of in the same theme, it would potentially be useful to support some lower speeds. It'd be one thing to support them standalone, but the main thing here is to support like the 10 gig and 25 gig interfaces, kind of downrating those to run at a lower speed. 1 gigabit per second support in particular could be quite convenient, because I know the White Rabbit project, I think by default right now uses 1 gig. I don't know if there's any White Rabbit stuff that runs faster than 1 gig. This could be particularly useful also on switch ports, if you got to plug in a couple of 1G devices to a multi-port switch. So questions are, what standards are there, and how to support some of these lower rates with minimal overhead, right? We don't want to implement a completely parallel data path running at 1 gigabit per second, if at all possible. Obviously you might have to implement some portion of it, but if we can use the same Mac and the same AXI stream interface and whatnot, that would be great. And we also don't want to impose any restrictions on the operation at the higher rates, right? We don't want to, limit how many channels can run at, 10 gig or 25 gig or something like that, if there's a channel running at a lower speed. So, yeah. So let's take a look at some of the standards that exist. So I took a quick look at both the Ethernet spec and also just kind of, what some of the Xilinx cores support. And these are kind of all of the standards that I found. So there's 1000 base X slash SGMII. This is AP10B encoded data at 1.25 gigabits per second. It's used for, so 1000 base X is used for, that's just your standard gigabit Ethernet over fiber. And then SGMII is the, PHY attach interface for, or one of the PHY attach interfaces for kind of your standard tri-mode Ethernet. So 10, 100, and 1000 megabit per second. So this one, if you support SGMII, then you can plug in one of these little tri-mode base T adapters. Well, these can either be 1000 base X or SGMII, depending on the adapter. 1000 base X ones only support 1 gigabit per second. The SGMII ones support all 3, plus the auto negotiation to figure out which one you're using. So that's one standard. 2.5G base X is basically 1000 base X overclocked 2.5 times. And the spec actually has some, it's actually not quite the same. There are some minor differences according to the spec, but the spec has provisions for, hey, if you want to take 1000 base X PHY and run it at 2.5 times the speed, if you make these couple modifications to the proper 2.5G base X protocol, then it's interoperable. So that's actually kind of interesting. It wouldn't be that much additional logic and effort to support this speed. But I guess the flip side, does anybody actually use 2.5G base X? I know some of these intermediate rates on twisted pair are somewhat common. I don't know how common exactly, but I've definitely seen switches and NICs advertised at 2.5G and 5G Ethernet over twisted pair, but I don't know about 2.5G base X. And then there's also 5G base R that I saw, and this one is literally just half rate 10G. So we can potentially support this right now using by changing the divider settings on the GT cores. So again, I don't know if anybody's using 5G base R, but it is pretty easy to support. And then there's also US XGMII, and this is a PHY attach for the NG base T stuff. So this one supports 10, 100, 1000, 2.5, 5, and 10 gig. And it's basically the same as, it's a similar idea to SGMII, where, except it's the 10 gig version. So it uses symbol replication to support the lower speeds. So that one is potentially relatively easy to implement because you don't need to change anything at the receiver level. It's just a few modifications at the PCS level. So the question then is, how many of these are actually useful and worth implementing? I don't know if you have any opinions on that. I thought I saw somebody come off of mute. Ulrich, were you going to say something? No? Okay. Did I see Julian come off of mute?
Yeah, I just put some message on the chat. That's why.
Oh, okay. I will take a look at that real quick here. I guess I don't have the chat open. Okay.
I didn't want to interrupt that. That's
Oh, that's fine. That's fine. Oh, so you're saying that 2.5 base X is commonly used for GPON ONUs. Okay. On the, so actually on the GPON side or on the other end?
No, on the GPON side, on the ONU, that's the client side.
Right. Okay. I see. Yeah, I guess there's
on the OLT side, you have some specific SFPs that are mostly just transducers. There is no intelligence in them, no smartness at all, and so on the total, it can do 2.5 gigabit per second, but for the whole clients, in fact. You have the tree has 2.5 gigabits per second for all the clients, but one client may get at most 2 gigabit. That's why you need more than one gigabit on the client side, because some of profiles can get more than 1 gigabit in GPON.
okay, I see.
It's yeah.
Right. I know PON is TDMA, so I guess with
Exactly.
2 gigabits per second, then you're getting, most of the time slot basically, or maybe even just
and
all of the time
GPON,
slot.
GPON is quite complex in the way you can decide in case of contention who is going to have the bandwidth. You
Right.
can have multiple profiles and say you have one, for example, professional profile that you can get some bandwidth reserved, and then the personal profile may share the rest. You can have a lot of complexity in this at the same time on the same tree. It's TDMA, like you said, so the system just share.
Right. Okay.
But
Interesting.
all the SFP that I saw on the ONU side, so the client side, none of them are 10 gigabit. Most all the one I saw can synchronize at 2.5 gigabit.
I see.
And that's all.
Because you need more than 1G, but you don't need more than 2.5. Gotcha.
Exactly.
Okay. Right. I guess the only downside about that is then you got to have hardware to actually take advantage of that supports the 2.5G speed.
Yeah,
So
and
in some sense,
actually,
it might almost make sense for some of these things to support running it at 5G or 10G, just because that's potentially more common.
And actually, that's what is going. That's what starts to happen now, because the 2.5 gigabit on copper is more and more common, and now you start to see some hardware that can convert one on the other, like external converters. And so more and more you can see that. That was not the case before. Before it was simple. When you put the SFP in a NIC, what happened? It was synchronizing in one gigabit.
Right.
So potentially, if you had a profile that was at 1 gigabit maximum, it was not a problem. But now that we can see some professional profile at more than 1 gigabit, then you were artificially limiting yourself.
Gotcha.
With that. And so now you start to see some NICs that are able to do that, to do this 2.5.
Gotcha. Okay, so it definitely seems like there are some use cases for 2.5G base X out there. Okay, well, that's good to know. I'm not sure if anybody else has any opinions on that, but we can certainly discuss that over on the Zulip channel. I did make a post on the Ethernet channel about that. So I guess another question then is, what standards exist, but also, how some of these might be implemented. So I know one of the problems, well, there's two potential approaches on the transceiver side for some of these. One potential method is to use oversampling. The other one is to actually configure the transceiver properly for the line rate. And the problem with some of the Xilinx parts is that they only have 2 QPLLs per 4 transceiver channels. So if we have to support 10 gig and 25 gig line rates, we got to use one QPLL for 10 gig, the other QPLL for 25 gig, which leaves no additional ones for other rates, except for the CPLLs. Unfortunately, Xilinx decided to save a couple of transistors in the GT channels, so the CPLLs have very limited divider settings, and as a result, they're basically useless, because if you don't have exactly the right reference clock, you won't be able to generate the line rate that you want. And it seems like most of the dev boards, most of the boards that support 10 gig and 25 gig, they seem to use 161 or 322 megahertz for the ref clock instead of 156. So at 156, the CPLLs will work and give you 1 gigabit per second if you put them in the right configuration. But at 161 or 322, you can't configure them properly. Why? Xilinx just didn't support enough divider settings in the CPLLs. So that means that I think the only option for most of these things is to look into doing some kind of oversampling. Now, I'm not sure if this is going to be feasible, so I'm going to definitely take a look, at least for 1000 base X, and do some feasibility tests just to see if we have a transceiver configured for 1 gig and another transceiver configured for 10 gig with some sort of, oversampling implemented in soft logic. Can they talk to each other? Can they talk to each other reliably? Not sure. If it does work, then this is potentially worth pursuing, so we can support operation at 1 gigabit per second. 2.5G base X at 2.5 times faster. It seems like oversampling might also be possible here, but again, I don't know if it's worth going through the effort of supporting 2.5G base X. Worth discussing that. But yeah, for that oversampling ratio, I guess we'll have to see if that injects a lot of jitter or something, or if that's reasonable to do. For 5G base R, you can either do bit doubling or you can change the GT dividers. So on the Xilinx devices, that's pretty easy to change the dividers. On other devices, it might be annoying to change the GT settings. So without changing the GT settings, you can bit double and accept every other clock cycle at the MAC level, and that'll support 5G base R. So relatively trivial change to support that link rate. But again, I don't know if anybody uses 5G base R, so maybe it's not worth thinking about. USXGMI, like I said, is basically just a PCS change, which does replication of symbols at the lower rates. So that wouldn't be particularly complicated to implement, and we don't need to change GT settings at all. And I guess I should also must mention SGMI does something similar. When operating below 1 gigabit per second, it replicates symbols. So same kind of thing with just a modification to the PCS, you can make SGMI work. The other thing I was thinking is that for the 2.5G and 1000 base X standards, what we can potentially do is use the 10G MAC and just adapt XGMI to GMII. And then we don't need to have a separate gigabit MAC or anything else. So if we add more features to the 10 gig MAC, we'll be able to take advantage of all that stuff at the lower rates. So at this point, I'm just kind of, doing high level planning, what makes sense, what's going to be possible, what's going to be too much effort, what's actually going to be interesting to try to implement. and also do some feasibility experiments for 1000 base X. Oh, I guess one thing I didn't mention is that the interesting thing about the Xilinx ultrascale parts is that the normal LVDS I/O pins are actually fast enough to implement 1000 base X and SGMII without having to use the high-speed transceivers, the GTH and GTY cores. So that means if you take some FPGA with like 500 pins, you could implement 100 ports at a gigabit per second if you wanted to without using any of the high-speed transceivers. That could potentially be an interesting use case for some kind of a switch, perhaps. I don't know, but we might take a look at that as well. I know Xilinx does have a core for that. They have their gigabit PCS PMA core, which can do 1000 base X or SGMII, and it can also support LVDS I/O. But if you're doing something like White Rabbit, you might need to dig down inside of that and do stuff closer to the transceivers. So I might need to take a look at that independently as well and see how hard it is to make that work. It seems like that core is actually pretty open because they're just using the device primitives. So might be worth taking a look at that as well, just to see kind of high level how that's supposed to work. So hopefully I'll be doing some experiments over that on this over the next few weeks. I'll definitely keep you guys informed if there's anything interesting going on. Okay, so moving on to a couple of other things. I know Carlos is looking at the TSN spec for some of the research that he's doing. So one thing that the TSN spec calls for is frame preemption, where you have two different traffic types, express and preemptible. And express frames can interrupt the preemptible frames to reduce latency. Now, there are some restrictions because the way the protocol is set up, it has to avoid, runt frames. So you can't interrupt the preemptible frames and produce a fragment that's less than 64 bytes. So if your preemptible frame is less than 128 bytes long, it cannot be interrupted. It cannot be preempted. If it's longer than that, then you can't preempt it in the first or last 64 bytes. Frame preemption, it uses modified preambles to keep track of the preemptible frames and the pieces of those. And it also uses a modified FCS to identify frames that have been preempted. And there's also a mechanism to detect dropped fragments. So you don't get, say, two preempted frames with a dropped fragment in between getting merged into one, which would be a problem. This is, like I said, part of the TSN spec. I'm not sure if
it's optional, Alex.
What?
It's an optional part.
It's an optional part. Well, I was gonna say, I
Yes.
don't know if it's if it predated the TSN spec or if this was introduced as a part of TSN. But yeah, it definitely doesn't seem to be required, but it is potentially worth looking into because I can definitely see that there could be some applications for this.
Yes, so, there is. It's just so like TSN is a bunch of specs pulled together.
Right.
And
I guess TSN spec is kind of a misnomer because there's
so there is profiles that bundles specs together for specific types of applications. So there is a specification that bundles together sub-specifications for automotive TSN applications, for example.
Gotcha.
And if you say our IP core complies to this profile, then everybody knows, okay, this and this is contained.
Features that are supported. Yeah, okay, got it.
Exactly. So there is a whole bunch of different portions of it forming something that's called TSN.
Right.
So
Okay.
the TSN, difficult.
Yeah, it's definitely kind of one of those kitchen sink kind of specifications. Lots of random stuff in there. But yeah, so at this point, I'm kind of taking a look at how this works and how maybe this could be implemented in Corundum because so Xilinx has their 1 gig, 10 gig, 25 gig switchable Mac core. And so I was taking a look at that as part of the previous point there. How do they do the 1 gig? Well, spoiler alert, they use the CPLLs for that. And as a result, they only support the 156.25 megahertz ref clock, which means it doesn't work on most of the boards that I have. But they also support in that core the 802.1 CM frame preemption. When you turn that on, now you get 2 sets of AXI stream interfaces for one for express and one for preemptible traffic. So, if we're going to implement this in the Corundum Macs at some point, then there's a question of, okay, how do you interface this with the rest of the system? Do we have to have 2? Okay, someone said 802.1 QBU. Yeah, so these standards are it's hard to keep track of them. I think the QBU letters correspond to like a draft standard before it gets integrated into the main one. I'm not sure. But I also think like the 802.1 is like one side of it, and then there's also a spec on the 802.3 side as well. So
Yeah, so
and I think they all kind of refer to the same functionality.
Yeah, from my understanding, the .1 specs are the functional ones, and the other ones are mapping this onto specific physical layers. So there is according ones for 802.11 for wireless applications as well.
Right, yeah.
So this is kind of the
complicated.
Yes, it does. And yeah, well,
I've noticed this also applies to some of the other protocol layer stuff, and it's like some of the 2-letter stuff sometimes kind of goes away as it gets merged into the main spec. So like,
yes.
For example, there's several different types of encapsulation formats for VLANs and related stuff. So that it's like 802.1 QBB or 802.3 QBB. I don't know, 802. Something QBB.
I guess the rule is if there is a new main standard release, then that gets pulled into the main standard, and then these substandards are thrown away.
Right. Yeah. So it's like, I think QBB was sorry, I was thinking VLAN tag. No, I think QBB is actually pause frames. Well, now that's just PFC pause frames.
and actually,
and then you got 802. something Q VLAN tags. And there's like 2 different versions of those, depending on whether it's just normal VLAN tags or the provider VLAN tags. And if you look at, I know Scapy has one of them as Q, and the other one is, I think, AD. And the AD comes from the kind of separate spec that was talking about those before it got merged into the spec. So it's a mess.
And it's sometimes just a reinterpretation of the same field. So it's not interpreted as a virtual LAN, but as a traffic class in the same LAN. And yeah, and that's something that might be used to actually interface those express traffic. So you can kind of, if you use the traffic classes, I guess you were thinking about implementing PFC, right?
Yeah, I guess that's that would be on kind of the classification side, right? To figure out what traffic class you're associating. And I think there's several different places you could potentially pull that from. And then the fun part comes, what if you have like 2 or 3 nested VLAN tags? Where are you pulling that that priority field from? Is it the outermost
one? Here your
one?
fun comes along.
Hey, yeah. Yeah, so not sure about that. But yeah. Yeah, that is one thing that the VLAN tag carries is the priority code point. So yeah, I guess sometimes you use those even if you're only using one VLAN. Anyway, yeah, so I've been taking a look at this to try to get my head just wrapped around how it works at a high level, and then the next piece is to figure out, okay, how would this integrate with the rest of Corundum? Not sure at this point, but starting to look into it. It'd be interesting. Yeah, again, like the other stuff, is there anybody interested in this feature that might be interested in helping to make it happen? I know Carlos is interested in that. Not sure if anybody else is. So figure I'll put this out here. We can certainly discuss this at some point if this functionality is interesting to anybody. Let's see. And then I guess I had one other thing here, right? White Rabbit and PTM support. So Corundum currently supports PTP, which that's good for kind of microsecond level time synchronization. But if you need better precision, well, I guess PTP can potentially get you down to a handful of nanoseconds, but White Rabbit goes much better than a nanosecond potentially. So for anybody who's not aware, it's a method for transferring time and frequency information over a network with very high precision. And it's basically a combination of synchronous Ethernet and PTP. So you use the links themselves to transfer the frequency information, and then PTP to do the time synchronization. And since the frequency information has already been transferred with the links themselves, it makes the synchronization more reliable. So it's quite useful in certain circumstances, but it does require some additional hardware in order to make this work. But the interesting thing is it looks like most of the FPGA's boards that support Corundum at the moment, I mean, with a few exceptions, actually have all of the necessary components to support White Rabbit. Although another component that's potentially useful and potentially more important if you're doing White Rabbit is something called PTM, and this is basically PTP for PCIe. So it allows you to sync the host, sync a clock on the host CPU to devices, using time stamping on the PCIe side. Unfortunately, it's a very new standard, so not very many devices support it. In particular, it's not supported on any Xilinx FPGAs at the moment. It's only supported on a couple of Intel FPGAs and only on the most recent Intel CPUs. Now, the interesting thing here is that the OCP project is interested in building a White Rabbit NIC. And for that, they need both White Rabbit and PTM support. Now, from my point of view with Corundum, even without PTM support, White Rabbit support would be quite interesting because, you can time sync that to, or you can make that timing information available to, the hardware on the NIC. But with PTM support, you can push that back to the host clock and very precisely synchronize the host clock. So on most existing targets, I think the only thing that you really need for White Rabbit to work is a tunable reference clock for Ethernet with PPM or PPB level tuning capability. So the SI570 parts, any board that has one of those for the reference oscillator, that works. Alternatively, the any of the Silicon Labs PLL chips, a bunch of boards use those. That would also provide, high enough resolution. If you have a fixed frequency oscillator, then it doesn't work. So there's a few boards that were like, hey, it would be nice to support White Rabbit on this board, but it doesn't have tunable oscillators. So the most annoying one, I think, is probably the KR260 SOM, or the KR260 board from Xilinx with the K26 SOM, where they use a fixed frequency 156 megahertz oscillator for the reference clock. If they put an SI570 down on there instead, that could be a pretty nice little White Rabbit node potentially. Unfortunately, that's not the case. Some of the other boards, on the other hand, this could potentially be done. So at this point, we're basically kind of in the planning mode, although I am going to mention here very briefly PTM about how this maybe could be implemented. So PTM, it requires not only exchanging PTM message TLPs, but also timestamping them. So I think right now the only devices that natively support PTM are the R-Tile Intel devices, so Agilex I and Agilex M. So very, very high-end expensive devices. It's not possible at all on the P-Tile because there is no transceiver access, and for H&L tiles, there's no transceiver access when using the hard IP cores. So on those, you would have to use a full soft implementation. On Xilinx devices, on the other hand, since they do use a hard IP core but soft interfaces to the transceivers, maybe there would be a way to extract the timing information from the PTM messages. Not sure. This potentially could require quite a bit of work in terms of basically building up partial PCIe RX PHYs on both the TX and the RX side to extract the PTM messages and timestamp them. But we also need to test to see if the core can actually pass PTM messages. If that doesn't work, then the only option is a full soft core, I think. So yeah, not exactly a straightforward thing to do, but it seems like there might be a path forward on Xilinx devices. And if so, that could potentially be a pretty cool capability, being able to take advantage of PTM, well, potentially in combination with White Rabbit, but I mean PTM by itself, or in combination with PTP, could be pretty useful even without White Rabbit. So again, not sure if there's anybody in the community that's interested in PTM and or White Rabbit, but it's definitely something worth discussing and seeing if we can get that working on any of the existing boards.
Alex,
Ulrich? Yeah,
I guess we should have a meeting about White Rabbit offline,
sure.
because it's definitely on our roadmap to build something like this.
Okay, sounds good.
And we already did some implementations on UltraScale Plus devices, which might be of interest in specific platforms.
Definitely. Yeah, there's also been some activity on an issue on GitHub where somebody else has been doing some work with Syncy, at least. I don't know about White Rabbit, but definitely Syncy on some UltraScale Plus devices as well. So sounds like they went the route of making a custom board, but potentially there's some odds and ends there that could be pulled back into the core as well. So yeah, definitely something worth discussing.
Yeah, so we are currently kind of building a reference for ZZU102. And that will be upstreamed in CERN. I think they use GitLab, but we can't push there. So that needs to go through their channels, and they are busy with a lot of stuff right now.
So this is just basically a straightforward White Rabbit implementation on the ZC102, not necessarily involving Corundum.
For now, that's White Rabbit, but it will be extended, and it uses special, currently not available topology for the frequency tuning. So it's built a little bit different.
What do you mean?
Yeah, so the clocking is implemented in a different way, and I guess we need to take this offline for now.
Okay. Fair enough. Yeah, I mean, I guess there are a couple of things that I can just mention really quick that may or may not be related to what you guys are doing. But so my understanding with White Rabbit is they use this scheme that they call DDMTD. I'm drawing a blank on what it means at the moment, to basically perform very high precision phase measurements on the FPGA between two different clocks, and they use that as the phase reference for basically building a soft PLL to do the phase locking. And for DDMTD to work, you actually need a frequency that's very, very close to the line rate, or very, very close to your reference clock, but different from the reference clock. So on a bunch of the early White Rabbit boards, they actually have two VCOs, one of them to produce the reference clock and one of them produce this offset frequency for the DDMTD. But it seems like that the PLLs on the FPGA are good enough. I don't know if maybe this wasn't the case when they were first building White Rabbit, or if they just didn't think about this, but the PLLs are good enough to actually generate this offset frequency if you cascade a couple of PLLs. So you actually don't need any additional external VCOs. You just need a single external tunable oscillator for the reference clock, and then from that reference clock you can generate this additional offset clock that's used for the DDMTD functionality. So with that, you don't need any additional hardware on most of the boards in order to implement PTM. Now, I'm not sure what scheme is currently being used on most of the White Rabbit hardware that CERN is making, if they're using the scheme on any of their boards, or if they're using the two VCO approach.
Yeah, from those design spin-offs that I know of, most of them have some sort of dual external tunable clock sources in various versions.
Right. Yeah. So that definitely makes sense if you want to stick as close to the White Rabbit stuff as possible. But in terms of, well, if we're going to make something that runs on existing dev boards, unless you're going to start retrofitting boards with oscillators and peeling off the reference oscillators and replacing them with VCOs and whatnot, it definitely makes sense to explore the possibility of using this internal method for generating the clock. And there was I did have some communication on one of the GitHub issues, actually, with somebody from the White Rabbit project who had some presentations on this technique. of using the internal PLL. So it's definitely something that they've looked at CERN, but I don't know how widespread it is in White Rabbit hardware at this point. But it probably makes sense from a cost perspective anyway. So if you're doing anything new, instead of putting down 2 VCOs, if you can save a whole VCO, that would probably be a good idea.
Yeah. So we didn't find anything in upstream repositories from CERN. But currently they're putting together a new, let's say, base system. So they were building this around some micro-based soft cores before, I think, and now they moved to RISC-V, and there's a lot of work going on there.
Gotcha. Okay.
So, and that's also what we use as a base. So we directly jump to the current development. You can't call it a branch. It's quite a lot of open ends that you need to stitch together to make it work. Yeah, so that's where we base on, and yeah.
Interesting.
No
okay.
public data for now. It will be public at some point, but we can share some data until then.
So
not
their
public.
code is currently not public, or
ours?
okay, gotcha. Well, can you say
Yeah.
if you're using any external hardware, or do you have to make any modifications to the ZC102, or is it basically just a stock ZC102?
No, it's a stock. It's a stock
Okay,
ref
gotcha.
kit. Yeah, no hardware
So
modifications.
you're not adding any VCOs to it.
No.
Okay.
Also,
Gotcha.
no FMC cards attached.
Well, right, yeah. Okay, gotcha. And this is using the GTH transceivers, presumably through the cages.
Yes, exactly.
I guess
Everything.
If you're not adding any FMCs, then you probably have to go that route. Because my understanding also is that White Rabbit doesn't work over like gigabit twisted pair Ethernet. It might work over 100 megabit or 10 megabit, but something about how the PHY layer works with the twisted pair PHYs, it doesn't work. But it does work with fiber. Like all of their stuff, I think, is 1000 base X at this point.
Yes.
Do you know if there's anything faster than 1000 base X that's being used for White Rabbit? Has anybody done it at 10G or 25G?
There are developments and development plans for it. Not sure where they currently are.
Gotcha.
Okay. We definitely aim at 10 gig as well.
Right.
But that's a longer term thing.
Okay.
I don't know how fast we can get there. Yeah.
All right. Well,
so
but the
that's
code
very
that
interesting.
you guys are basing the design on, that is publicly available from CERN, right? Or is that still, are they keeping that?
No, that's so we used we started off from I don't know, it's one of the branches that seemed to make sense for us. Gotcha. And then added pieces from all over the repository and fixed some items and made it work. So we currently have a setup where two ZCU102 synchronize against each other. We are in contact with CERN, providing patches to them. But as I said, they are way heavy loaded, so it didn't make it into the repositories yet.
All right. Well, I'm sure it'll end up in there at some point. But yeah, I mean, at this point, we're still kind of in the planning phase on this end, and I have been interfacing with some of the folks on the OCP project, and I think they are interfacing with some of the people at CERN that are involved.
Yeah, maybe it makes sense to gather around together and just sync up and see where we are and who wants to do what anyway.
That would probably make a lot of sense. Yeah. All right. Well, I guess. All right. Yeah, we can certainly discuss that. Maybe I can create a new White Rabbit channel on Zulip, and anybody interested in White Rabbit, we can have a discussion there. I don't know. I don't know if CERN has any channels, or if that's all done via email and GitLab issues or something.
They are building up something that I guess, will be released to public in the autumn this year. So there will be some collaboration community stuff built around White Rabbit, as
Gotcha.
they see more adapters evolving in industry as well as in science applications. And yeah, not sure how this will work out and how this will look like. We talked to them, or actually they reached out to us because they noticed that we were starting providing patches and working with White Rabbit, and that's just not settled yet. So there will be something started most probably this year,
Gotcha.
because right now it's basically a couple of people at CERN managing this development.
Right.
Yeah, and they are heavily loaded with building new hardware, right? So this is not, these are not fully dedicated to developing the HDL and software components. They build these systems they use to run the accelerators.
Right. Yeah. No, that makes a lot of sense. And I mean, I guess that's something to. I guess that's kind of an aspect of a lot of the stuff that they do is that, or at least historically, they've had to build not only the HDL but also the you know, the cards and the hardware that it runs off of. Right. That was a whole thing with the White Rabbit switch project. They got to build their you know, FPGA board with all the transceivers and VCOs and whatnot to run White Rabbit in order for that to work. But
exactly,
if we can take that functionality and hopefully make it run on, you know, existing dev boards, then that eliminates the issue of having to make your own hardware. If you can just buy an off-the-shelf board and just drop the design on there, then that's a good starting point.
Yeah, so that was something, yeah, we noticed as well. So when we wanted to start and play around with it, it's really, it's not an easy start because there is no board out there that you can just buy somewhere off stock and say, okay, let's start with it.
Yeah,
there are some
and CERN
some
is
very
not in the hardware
specialized
business.
companies.
they don't
Well,
sell it.
That's right. And there are some very specialized companies that sell it. So they usually license those out or have their partner companies actually producing the hardware. So there is one or two Czech companies, I guess a Polish one, and there is one in China and a Spanish one. But they are kind of used to sell into these scientific markets.
Right.
And at least my attempts to get into contact were never answered from none of them.
Annoying.
So it's not so easy to go to Mauser and buy a dev kit and say, okay, just, I don't know, build the bitstream somehow, as complicated as it could be, and then load it and play with it, right?
Right.
So yeah, and I guess lowering this barrier to entry makes sense for the White Rabbit project as well.
Definitely. Well, if we can get this thing integrated into Corundum, then that could be really good for the White Rabbit project as well, because, you know, you could just download that, build it, and run it on, you know, an Alveo board and have a White Rabbit node operational. Because I think most of the Alveo boards, potentially all of them, should be able to support White Rabbit. They all should have tunable oscillators on there of some sort that's accessible from the FPGA. So yeah, that would be huge.
Yeah, I haven't looked
because
at these
you can
boards,
buy
but
those from
yes.
DigiKey and Mauser and whatnot. They're not necessarily cheap, but you know, well, I mean, some of the boards are pretty cheap, right? I think they're I did notice that the Varium C1100 blockchain accelerator board, which is a U50 effectively, except with double the HBM and 2 QSFPs, those are like, well, I think the price went up a little bit. They're a little bit more than $2,000, but the lead time is like 4 weeks now. Last when I checked on those a couple of months ago, the lead time was like 50 weeks or something. I'm like, dang. But if it's 4 weeks, okay, you know, that makes that a much more interesting card to work with, and you know, for the price. And if that can support White Rabbit, which I think it can, it's got a PLL chip on there for Synchy, but you should be able to use it for White Rabbit, I think. That could be a pretty good platform. So
Yeah, sounds good. Yes.
Okay, just to mention that Well, I would like to also be involved in this development, but maybe after we have something working on for the Switch. So after that, I would also like to collaborate with it.
Yeah, sure.
I think I will get into it also, but when I get better in Verilog and all of that.
Right.
Um,
Okay.
By the way, the problem on the U50 is that the crazy access to the I2C bus. I don't know if you remember that, but there is
Right.
some. You have to go through some kind of microcontroller because the lines
Right.
are
Yeah.
not
Yeah.
routed through the FPGA
Yeah. Yeah. Yeah.
itself.
Yeah. All of the new Alveo boards are like that. Yeah.
Yeah, and that's crazy. I don't know what they did, but it's a stupid thing. So that's complex because some SFP needs to be
Oh,
configured.
right. Yeah,
separately.
no, we have a need for that as well.
Yeah.
Because we need at least to poke at the CDR control registers on
Exactly.
on just normal QSFP modules. But yeah, if you need to poke at something more complicated, uh they have made some changes to that protocol. I remember in the initial version of it, you could ask for a readback of all the registers and you could write to a small window. But I think
Yeah.
they've expanded it to where you can write to the whole space now. But I think only on the one address, right? Like just at I2C address
Yeah.
50. If a
And
module
and the
pops up
problem,
multiple addresses, you can't poke at those. So it's like, come on, guys, really?
yeah, yeah, and that's stupid because there is a lot of SFPs that needs non-standard addresses access,
Yeah,
especially the GPON stuff. For example, you can talk to them via I2C on, of course, non-standard address since it's a Linux on the other side.
hmm
So sometimes
running Linux on a transceiver. What do they think of
yeah,
next?
it's crazy. If you watch in them, it's a very tiny, often Marvel or Intel chip that run a full Linux in it.
That's crazy. Yeah. Yeah. So from that
And
standpoint, yeah, that's definitely a problem with those boards. But the PLL chip, fortunately, on those boards has a separate interface to the FPGA. So
yeah,
they basically just give you the PLL chip and you can do whatever you want with that. So that's good.
that's
That
good.
means, White Rabbit should work. But yeah, that's definitely an issue for other transceivers. I mean, I guess they do that. The annoying thing about those boards is they assume that you're going to be using the the Alveo framework and the XRT software and whatnot to talk to them, and that who wants to talk to the transceivers? You're just going to be running your ML AI application on there, and that's it. But
Yeah,
there are people like us that sometimes need to do weird stuff with the network side, and also who don't care about the Alveo framework because Corundum doesn't work with it. It's no good for
exactly.
networking. So yeah, in that case, well, now we have to deal with their stupid MSP 430 thing. Talk about the other hilarious thing is that the IP core that interfaces with that is a microblaze. So you get this hilarious Rube Goldberg contraption where you talk to the microblaze, which then goes and talks to the MSP 430.
It's crazy. I agree with you. But
yeah, it is what it is.
at this point, yeah.
Just my point with those cards is they're a reasonably good value if if
Yeah,
the
that kind of
MSP 430 is not a problem for your application. Oh yeah,
Yeah.
those blockchain accelerator boards also have a built-in USB JTAG, unlike the U50. So that's nice.
That's interesting because it's for $500 for just the probe, and
Yeah, it's stupid.
it's stupid.
Although I was doing some poking around on the one that I have, and I have the pinout, I think, mostly figured out, but I tried making a cable and it doesn't work. So I think there's a pin that needs to be pulled to ground or pulled to power or something. Haven't had a chance to do another pass at that. But yeah, that would allow you to use a normal Xilinx JTAG cable. The other thing that I noticed is that the board that's inside of their JTAG cable actually has a footprint for a normal Xilinx JTAG connector on it. So presumably, if you populated that footprint, you could use a normal JTAG cable through it. I mean, obviously that doesn't help with the price because you have to have both, but it is a data point for, well, maybe you could make a passive adapter for, you know, a couple of bucks. That would work. But yeah, it's even better if they just put the Frappin FTDI chip directly on the board with a USB port, so you don't need that cable at all. Although I guess the other thing about that that JTAG cable is they actually have JTAG for the MSP430 as well. So you know, there's 2 USB ports on there. One of them is for the FPGA. The other one has a different FTDI chip that's for the MSP430. So haven't had a chance to play around with that at all.
We could reprogram also the MSP430.
Yeah. Yeah, I think so. Now I don't know exactly what it's all hooked up to. Obviously the optical modules, you know, the Icebridge C bus. I don't know if it has any role in power management or anything else, or sequencing or something.
I see at least there is some fan control and detection of speed. Oh, I think I've
Well, yeah, but there's no fan on the U50, so
no, but yeah, I know, it's crazy, but that's what is written in the
right. It is in the yeah, that does get read out.
There is two. I
over
think
the
there is
register
two
interface.
versions of the U50. One with a fan and one without. At least that was the case at the beginning.
I think the reason the fan control and whatnot is in there is because all of the Alveo boards report the same register space. So I don't think they've never made an active version of the U50, but the U200 and U280 and U250 all have active versions available that have fans. Although Xilinx's firmware is buggy, occasionally these things will ramp up to 100%, 100% throttle, if you will, take off thrust, and not want to come back down to something at a more reasonable volume. Although that could be more of an issue with my VCU 1525, which is older as opposed to the Alveo boards. So maybe it's not a problem with the Alveo boards, but the VCU 1525 is basically pin compatible with the U200. So it's effectively an Alveo board. Anyway.
Okay. Interesting. I did not know the blockchain as record card.
Yeah, it's I don't know why they had to obfuscate it like that, but
exactly.
Yeah, it is. So the 2 new Alveo boards, well, new-ish, the U55C and the C1100. I call it an Alveo board because it is an Alveo board, effectively. They are basically the U50 and the U280 in a different package, right? A different form factor. So but yeah, the price of the C1100 really makes it an attractive board because it's even cheaper than the U50, but it's better than the U50. So it's like, why would you even buy a U50 unless you need the half-height card? Oh, it also has double the HBM. I don't know if I mentioned that. 16 gigs instead of 8 gigs on the U50.
Interesting.
Good. So I'm just looking at the Varium C1100.
Yep.
And it says it has 800 lookup tables. Does this make sense?
It's the same FPGA as the U50. It reports the same JTAG ID.
Okay. So that's possibly a typo, right? Because 800 lookup tables. That's like 20 years ago.
It's the same part as the U50. So
okay, makes sense.
I'm not sure what that's in reference to.
Yeah, that's possibly kilo lookup tables.
Could be, yeah. Is this just the product page for the C1100? I'll see if I can pull it up.
It says 872 lookup tables and 1,740 registers. It seems.
Yeah, those have got to be in thousands. that makes no sense.
Yeah.
But this is like a, I don't know.
Well, all of the dorking around with PCI Express stuff has definitely made me a little bit more suspicious of the Xilinx documentation than I was previously.
Yeah, you're right.
No.
The U50 is 870K.
Yeah. And I have the data sheet here.
Yes. They are just missing the K in after the number.
Yeah.
Well, what's the
872K.
difference? It's just one digit, right?
Yeah, really. 872K LUTs, 1,743K registers, 5,952 DSP slices. Yeah. 24 GTY transceivers. Well, I mean, I think it's like the U50 where it's actually one of the VU35P FPGAs probably with all the transceiver sites locked out except for 24. Although it might lock out different ones than the U50. Not sure. I think that's the case with the U55C versus the U280 is that it actually uses different transceivers. They're not pin compatible. It is the same FPGA with different HBM in the same package, reporting the same JTAG ID, but there are some board level differences. Yeah, and then obviously
And you
these all
can
have the
even
same.
mine Bitcoin when you don't use it.
Yeah, that's true. It'll pay for itself.
Yeah.
Well, in a while, I guess it
Or-
also
or
depends
not.
on what the
It
price
depends.
does, which I think has been going recently, right? For a lot of the cryptocurrency. Yeah. Yeah, I mean, this one is quote unquote for blockchain stuff, but there's nothing really particularly special about it. So it seems
Yeah.
like you might be able to, if you have a bunch of FPGAs lying around, you could potentially use it for that sort of application. In fact,
Yeah.
it might even be better to use some of the like U200 cards. I think those have a much larger power envelope than these things do, right? More cooling capability, more power supply capability. Although on the flip side, I think some of the miners are actually more concerned not with overall power, but with power efficiency. So if you get something like one of these C1100 cards, they would actually undervolt it or whatever to try and get more efficiency out of it, which is interesting. It's nice from an environmental standpoint, right? I know Bitcoin is horrible from that perspective.
Yeah.
Oh man.
No. It was just a joke. I think my company wouldn't like that too much.
Yeah. Well, I mean, considering the cost of some of these cards, I'm sure people do that.
Maybe.
All right. Well, is there anything else that we want to discuss? Any other comments on those alternative line rates? Anybody interested in 40G Mac who wants to write some HDL? Maybe not. I don't know. Anything else we want to discuss or? Nope.
I guess there's one thing maybe that there is something called QSGMII where you can connect four.
Oh right, yeah.
There are files that kind of bundle 4 SGMII data streams into a single one that's clocked 4 times faster.
Yeah. I think there were probably 2 standards at least that I was aware of that I didn't mention on that slide. There's QSGMI and there's also, I think, a multi-port version of USXGMII, which is kind of a similar idea. And I didn't mention those because I'm thinking more in terms of, something you can stick in a QSFP or an SFP slot to adapt something. These I think are more kind of standards for boards. But it's definitely potentially useful to think about in terms of, would it make sense to implement something like this? Because I know you guys were screwing around with the QSGMII and we're having some problems with that, if I recall correctly. But
yes, you do.
Yeah, I mean, I guess that's something if you're building a custom board that could be useful. But the thing that complicates those is that you have, multiple Macs feeding into one channel. So that becomes a little bit more complicated in terms of how do you support that at an architectural level. So
Yes.
Yeah, single port ones, okay, that's pretty straightforward. You just slow it down potentially to run at a lower rate. But yeah, the multi-port ones, I mean, I guess similar to the frame preemption thing, where you might need a separate data path coming in or something, and they can't block each other. So
Yeah, and at least designing IP cores seem to be quite simple. It just provides 4 GMII interfaces internally, and it used 1 transceiver channel.
right.
So that's pretty straightforward. You just implement 4 Macs, hook it up to this kind of PCS layer, and then it takes care for you when it works. So we skip this.
I was just gonna say when it works.
So for us, we couldn't bring the PHY up running with this.
Okay, so I guess it was unclear if it was like a PHY problem or a core problem or a board problem or
Exactly.
something wasn't working.
We just so we foresaw something like this, and on our custom PCB we provide an SGMII channel for each PHY separately, and we fall back to this one.
Yeah, I guess it's nice that it's simple, but if it doesn't work, then what's the point?
Yes. Yeah, so it will
I
work.
do not
for
expect
some.
that it's that simple.
Yeah, I wouldn't say that the PHY doesn't work, because there are evaluation boards that are built around it, where they have, I don't know, a switch chip, I guess, that's interconnected to one of these multi-PHY chips via QSGMI. So I think it will work somehow, but at least not for this setup we had there.
I mean, this is potentially one of those things where there's about 2 million registers inside of these stupid PHY chips, and if you don't poke all the right ones, it doesn't work. Figuring out which ones to poke is potentially an exercise in frustration. So yeah, it's possible that if you talk to the manufacturer of the Rabbit and PHY chip and they say, oh, you just got to poke this register and that register, and you only poked one of them, well, that would explain it. But good luck getting one of those guys on the phone.
Yeah, that could have been a problem.
Yeah, I mean, did it work at all, or it just like you could sometimes make it work, or it never worked? Never got any links up, never got any data flowing.
I actually don't remember anymore. I need to dig out
was a while ago.
the issue that we have updated internally and tracking this. No, yeah, that's I don't know, 1.5 years ago.
All right. Well, I mean, we can definitely discuss this sort of stuff on the Zulip channel outside of the developer meeting. So if anybody has any questions or comments or thoughts on this sort of thing, feel free to go post. I think I posted some stuff in the Ethernet channel in terms of these potential additional link rates. So yeah. Anyway, I guess we've probably about exhausted all of the topics for today. So thanks to everyone for tuning in, and we'll see you in a couple of weeks.
Okay, see you.
Thanks a lot,
Okay.
guys.
All right,
Bye.
talk to you.
Thank you.